Hello. Today, as we start to rationalize radicals, what that means is to make it rational, and we want to get rid of the square root because the square root is what's making it irrational. That's our goal, is to get rid of square roots, or cube roots. Some of them are cube roots too. Now, to get rid of a square root, what we need to have is what we call a perfect square sitting underneath that radical. So the first thing I think we're going to probably need to do is have a list of perfect squares. And you might want to jot this down on in your notes so you have it. But let's just get started. We're going to take a 1 and square it. Well, that just equals 1. So 1 is considered a perfect square. We could take 2 and square it, and we get 4. So 4 is a perfect square. If you take 3 squared, you'll get 9. 9 is one of our perfect squares. And I can just go down this list and keep making these perfect squares. And this, of course, would go on forever, but it's nice if you know some of the perfect squares just off the top of your head. Now, I could keep on going, but ultimately it's just I take any number and I square it. That's going to be a perfect square. So these right here are all of our perfect squares. Now, I'm also going to do the same thing with the perfect cubes, because we're going to need that later on in the lesson. So if I take 1 and cube it, 1 times 1 times 1 is 1. 2 cubed, that's 2 times 2, which is 4, times another 2 is 8. 3 cubed, that's 3 times 3, which is 9, times another 3, that's 27. So that's a perfect cube. Let's go one more. 4 cubed. 4 times 4, that's 16, times another 4, that's 64. These are all of our perfect cubes. So anytime we're dealing with a cube root, we need to get one of these numbers to sit underneath that radical so that it'll become rational. All right, so keep that list in the back of your head there as we move forward. All right, let's get started. Our first example here, we're trying to rationalize the denominator. That means we need to get that square root of 19 out of there. We don't want a radical down there. To do that, I'm going to multiply by something that's going to make that a perfect square. So 19 times something to create a perfect square. Well, I'm just going to take 19 times 19, because that's going to get me 19 squared, and I don't know what that is, but I know it's a perfect square. And then up here, I'd have that. Remember that you have to take it times the numerator and the denominator so that you keep this fraction the same. Negative 3 square root of 19 is what I'm going to have in my numerator. In my denominator, I have the square root of 19 squared, whatever that is. But it doesn't matter because the squared and the square root are going to cancel each other out. Those are opposite operations. I'm left with a negative 3 square root of 19 all over plain old 19, and my radical is gone. Now, we're always going to try to reduce after we rationalize, and what you're looking to reduce are like things. This 3 and 19 are both outside the radical, so they could maybe reduce, except that they don't. These 19s seem like they would, except this one is in the radical, this one is not. You do not get to reduce that way, only like things. So I'm done. I'm going to call it quits with my answer right there. Now, let's try again. This next one, I have a square root on the top also. The thing that I want you to be looking for on this is that the square root of 32, way back in section 9.2, you learned how to reduce radicals. The square root of 32 can reduce, and we want to get anything that's in the radical as small as we can before we start worrying about rationalizing. In this example, I'm going to take this square root of 32, and I'm not going to spend a lot of time on the reducing because you've already done that in 9.2, but I know that 16 times 2 is equal to 32, and 16 is a perfect square, so I can kind of reduce that square root of 32. It would become a 4, because the square root of 16 is 4, root 2. My denominator is still that root 7. It didn't do anything for me there. All right. I'm just trying to get my number smaller. Now I'm ready to do that rationalization. I'm going to multiply by something here. Well, 7 times 7 is what I want to multiply by. That'll make a perfect square. Same thing in the numerator. Multiply by root 7. You can only multiply like things, so the 4 is just going to sit there, but the 2, the root 2 and the root 7, they do get to multiply because they're both underneath the radical. So that's going to end up a square root of 14. In my denominator, I have the square root of 7 squared, which is just going to cancel, and I'm probably not going to even bother writing that anymore. If I'm going to multiply two radicals that are identical, I'm just always going to get that number. I'm going to take a glance to see if I can reduce the 4 and the 7. I cannot. Can't do this because one's in the radical, one's out. I'm good to go right there. That's my answer. Okay, let's try one more time. On this one, I wanted to show you what happens. This one, you can kind of see that the fraction is all underneath the radical. Well, this is no different than seeing it as a square root of 27 over a square root of 2. You're just taking the square root of both of those. You can write that either way, and you're going to see both ways on your homework. If I go ahead and leave it separated like I just did, the next thing that I notice is that this square root of 27 here is too big. That can reduce for me, and I'm going to take the time to do it. That's going to reduce to a square root of 9 times the square root of 3. 9 times 3 is 27, and the reason I chose that is because 9 is a perfect square. It's just going to be a 3, square root of 3. My denominator is still square root of 2. Now I'm ready to rationalize. Multiply by itself, top and bottom. I'm left with a 3 square root of 6 over 2. Nothing reduces. I'm done. I'm going to keep doing some more of these practice problems. Each one is a little bit different, has a little different little thing to think about. Again, remember on this what I said on that previous one, where this is really the same thing as a square root of 22 over 14. You can write it either way. Okay, if you think about it here, the reason I might like it like this second method is because a 22 over 14 can reduce. Those are even numbers. I'm going to go ahead and reduce that fraction. 22 could reduce by 2, that'd be an 11. 14 could reduce by 2, that'd be 7. So I'm going to clean this up, make my numbers smaller again. Square root of 11 over a square root of 7. Now I'm going to work on rationalizing, multiply by the same thing that I have in the denominator, root 7, root 7. I'm left with a square root of 77 over 7. Nothing reduces. I'm done. All right, last one like this. Again, think of it. It's the same thing as a big fraction, and the reason I do that is just because I know a 28 and 21 can reduce. 7 goes into both of those. 28 divided by 7 is 4. 21 divided by 7 is 3. This simplified would look like this problem. Now the square root of 4, did you see that? A square root of 4? That's beautiful. That's exactly what I want to have happen. I want a perfect square to land under there. 4 should be in your list, in your notes, of all your perfect squares. The square root of 4 is just 2. So I managed to get rid of the radical in the numerator entirely. Although, remember, I'm trying to rationalize the denominator, so I'm still going to multiply by my root 3, root 3. So I'm left with a 2 root 3 all over 3. Done. Always look to try to reduce things and get your numbers smaller before you worry about the rationalizing the denominator part. I have one more of these. I thought it would be good to do one where that has some has some variables in it because it does that to you on your homework. The thing with the variables are that you wouldn't want something like a square root of x. What you want is you want this to be a perfect square. What I'd like it to be is a square root of x squared, because a square and a square root can cancel each other out, and that would just get me an x. So that's how we're going to deal with the variables. Now, on this problem here, first thing I'm going to do is try to reduce things. And what I see here is, again, I don't care if you take the time to separate these or if you just recognize that they can be separated. But what I'm noticing here is this square root of 4 that's going on. That can clean up. Now the y cannot. The y is still going to be stuck underneath that radical, but I can square root of 4. So I'm going to clean it up. The square root of 4 is a 2, but the y is still going to be in the radical. Denominator does not clean up. It's still a square root of 5x. So that's what I'm going to multiply by. I'm going to multiply by itself. 5x, 5x. In my numerator, I can multiply like things, so the 2 is going to be by itself, and in the radical, I'm going to have the 5, the x, and the y all underneath the radical. And we typically would always put a number first, and then we put the variables alphabetically. So I'm going to write 5xy rather than y5x. In my denominator, this is really going to be like a 25x squared. That's going to be a perfect square that's just going to come out to itself without the radical, 5x. Nothing reduces. I'm good to go. All right, so that's square roots. Let's look at some cube roots. Cube roots are the same idea, except that you want to have perfect cubes. So you have your list of perfect cubes. 2 cubed is 8. 8 would be a good number to have. 27 would be a good number. 40 or 64 would be a good number. All those are perfect cubes. So instead of trying to get like a 3 squared or an x squared, what I really want is to have a 3 cubed that I can cube root. And then those cancel each other out and I just get a 3. That's what I want to have happen. So in this example here, I'm going to go ahead and separate it since I've been doing that all along. And then I'm going to multiply by something to get a perfect cube. So 3 times, well, you can think of it a couple ways. You can think of it as, well, this is a 3 to the first, so I need a 3 squared. That way I'll get a 3 to the third. I'd have 3 of them there, and that's what I want to have happen. You could also look at this 3 squared and just call it a 9, and 9 times 3 is 27. Either way, I'll go ahead and write it like this for right now. Now in my numerator, I'm going to have a cube root of 4 times 3 squared. 3 squared is 9. 9 times 4 is 36. In my denominator, I'm going to have the cube root of, and I can write it as 3 cubed. That would be one way to write it. I could also write it as the cube root of 27, because that's 3 times 3 squared. Either way, I'm going to end up with this being a perfect cube, which is what my goal was, and my numerator is just going to be stuck with that cube root on it. And I'm done. Okay, let's try this other one. It has a variable on it. I'm going to separate it. Cube root of 3, cube root of y. I need to multiply by a cube root of, how many y's do you think I need to put in here? Because I want it to be a perfect cube, so I need 2 more of them. So there'll be a y cubed then. Do it in the numerator as well. I'm left with a cube root of 3y squared in my numerator, and in my denominator I have the cube root of y cubed. But again, I'm not going to worry about writing all of that. The cube root of y cubed, well, I am going to write it, and I'm just going to clean it up, sorry. I'm going to change colors. So this is going to end up cube root of 3y squared over y. Cube root and cubing undo each other. There's your final answer. All right, this is the last cube root example that I have. And this one, again, remember before you get started, you want to try to see if anything will get smaller. A 54 and a 10, because this is ultimately the same thing as this. I could reduce 54/10. They're both even numbers. Let's divide them by 2. 54 divided by 2 is 27. 10 divided by 2 is 5. This is really the cube root of 27 over the cube root of 5. Now, I like that my numbers are smaller, but did you see this right here? I have a cube root of 27. Isn't 27 in my list of perfect cubes? What is it that we cube to get 27? 3. So the cube root of 27 is just 3 over cube root of 5. Now I'm ready to actually rationalize. I'm going to multiply it by, I've got a 5, but I need 2 more of them, so you can write 5 squared, or you could write 25, either way. And I'm running out of room, so I'm going to go this way. I'm left with the cube root of 5 cubed, which is 5, and in my numerator, 3 cube root, and go ahead at this point, go ahead and call that a 25. Don't enter that into Hawks as a 5 squared. I'm not sure it's going to like that. Go ahead and just call it 25 at that point. All right, here's where it starts to get crazy and fun. If you look at this one, now my radical has this subtraction sign down there. We actually have a binomial. We have 2 terms in the denominator separated by that subtraction sign. Now, this is a different deal. I can't just take this and multiply by the square root of 6. Let me show you what would happen here. If I take the denominator times the square root of 6, since this is a binomial, that would have to get distributed. And right here, that would work beautifully. That's the square root of 6 times square root of 6. I'm going to end up with 6. But when I try to distribute it over here, I'd have a 7 square root of 6. And at that point, all I've done is shifted the radical to a different place in the denominator, and I haven't gotten rid of it. So we will not be doing that. What you're going to do instead, anytime you have a binomial, you have 2 terms down in the denominator, you're going to multiply by the conjugate. All right, the conjugate is that exact same binomial with the opposite sign. Let's try it. Let's look at what happens here. I'm going to take this times the conjugate, so it's a 7, but instead of a minus sign, I'll put a plus square root of 6. And again, whatever I do in the denominator, I'm doing it also in my numerator. In my numerator, I'm going to have a 5 that I'm going to have to distribute through those parentheses. Let's see what we would end up with there. That would be a 5 times 7, so that's 35, and a 5 times root 6, 5 root 6. Now here's where it gets fun. Look at our denominator. We've got a binomial times another binomial. We're going to have to do FOIL on that. All right, we can do that. FOIL. Multiply the first. 7 times 7. Then outer, 7 times the root 6. That's a positive 7 root 6. Now we're going to multiply the inner. Well, it's still a 7 and a root 6, but this sign is minus, so it's going to end up being a minus 7 root 6. And last is going to be a negative times a positive, so it's a minus root 6 times root 6 is 6. Now what's important to notice here is what happened on your outer and your inner. You got the exact same thing because we chose to use the exact same numbers, but one's a positive and one's a negative because we chose to use the opposite sign. That will happen every single time you multiply by the conjugate. That's why we do it. Because I'm going to be able to cancel the 7 root 6 and the negative 7 root 6. They cancel out. And that's how I got rid of my radical. Now my numerator is 35 plus 5 root 6 over 49 minus 6. That's a 43. Now something to look for as we try to reduce, before I box that in I should have talked about this, but when you try to reduce, since this entire fraction is being divided by the 43, the only way you can reduce is if the 35 reduces and the 5 reduces with the 43. And it doesn't in this case. This one has 2 radicals in the denominator. Let's see what's going to happen with that. I'm still going to jump in and try to multiply by the conjugate. So now it's a root 6, but instead of a minus, it's a plus root 3. Do it in the numerator as well. Think of these as binomials. We're going to be doing some FOIL and such. For my numerator, I'm going to take 3 and distribute it. That would get me a 3 square root of 6 plus 3 square root of 3. In my denominator, I'm going to have to do FOIL. I have root 6 times root 6, 6. Root 6 times root 3, that's a positive root 18. Inner is a negative root 18. Yep, that's what I wanted to have happen. And last, got a negative root 3 times a positive root 3. So negative times a positive is a negative, and a root 3 times a root 3 is just 3. And just as I anticipated, those are going to cancel like I needed them to. My numerator is 3 root 6 plus 3 root 3 all over 6 minus 3, that's a 3. And before I box that in, I'm going to look to reduce because I see a lot of 3's there. Remember that this term has to be able to divide by 3 and this term, but they do because they both have a 3 as a coefficient on them. So if I could do the 3, it will divide by 3, and this 3 divides by 3. Remember, you can't reduce with the things that are in the radical, but here I sure can. So that's going to reduce to a 1. That's going to reduce to a 1. So you can kind of show that it reduces to 1, 1, and 1. Final answer then just ends up being a root 6 plus a root 3. No sense in even writing it over 1. Let's not write it as a fraction. Whew, this is a long lesson. I'm sorry. I know, there's just a lot of different things. This is our last one though. This time I'm doing this with a radical in the numerator as well. But even before I do that, gosh, these are big. The square root of 17, that's huge. How I'm going to try to reduce that, I'm going to get some big numbers. But I'm stuck with a 17 because it's prime. But 18, I can reduce that square root of 18. Remember from lesson 9.2 that you can reduce radicals. I'm going to break this down into a square root of 9 times a square root of 2. That's going to get me actually a 3 root 2 plus 10 over root 17 minus 6. So I've gotten a little bit smaller. Now I'm ready to do my conjugate thing. So I'm going to take everything times the square root of 17 plus 6. Multiplying here. All right, this is a lot of FOIL. I have to do FOIL in the numerator and the denominator. Here we go. We're going to take 3 root 2 and multiply it by a root 17. Okay, that is 3 square root of 34. Then I'm going to do outer. 3 times 6, or 3 root 2 times 6. That's going to be an 18 root 2. Now let's multiply inner. 10 times root 17. These are all positive because everything was a positive up there. And now last is the 10 times 6. That's just a 60. Ooh, that's a lot of stuff up there. Okay. Now in the denominator, that's the one that I need to come out nice. I know my numerator's a mess, but I'm kind of stuck with it. Let's hope the denominator's better. When I do FOIL, I'm going to take my root 17 times root 17. That's just 17. Outer, a root 17 times a 6, that's a 6 root 17. But look at my inner, a negative 6 root 17. Those are going to drop. That's what I need. I have a plus 6 root 17, and I'm going to have a minus 6 root 17. And then the last is the negative 6 times the 6. That's a negative 36. Okay, as I needed, those are going to cancel. Okay, I'm sorry for the numerator. I don't know what to tell you. It just is what it is. No way to clean that up. It's going to stay these 4 ugly, radical, messy terms, and I just write them. And it is all over 17 minus 36, which is actually a 19, a negative 19. All right, that is not going to reduce. The only way it would reduce is if all these coefficients could reduce with a 19, and none of them do, so it doesn't even matter. I'm done. That's what I actually have to enter into Hawks. All right. Hope this helped you.